In our last explainer, we discussed ULP and subnormals. Today, we're going a step further. We're launching a full-blown forensic investigation. Get ready, because we're about to go deep inside the processor, to a place where the math you learned in school, well, it just completely breaks down. A world where the fundamental laws of algebra don't always apply. You know, we all think of our computers as these perfect, flawless calculating machines, right? But here's the thing. Inside the actual physical silicon of your CPU, those absolute laws of mathematics, they're forced to make some serious compromises. What we're going to uncover today are the consequences of those compromises. These strange glitches in the matrix, where numbers start behaving in ways they absolutely shouldn't. And here it is, our central mystery, the associative property. You know, A plus B plus C is the same as A plus B plus C. It's like Math 101, it's a bedrock of algebra that we all take for granted. But inside a computer's math coprocessor, the floating point unit, this is just false. No, seriously. The order you add numbers can completely change the answer. So how is that even possible? Well, let's go find our prime suspect. Now, the culprit here isn't some sloppy coding or a bug in the software. Nope. The root cause of all this madness, it's a feature of the hardware. It's a physical limitation, something I call the 23-bit constraint. Okay, so let's pop the hood. This is how a floating point number actually lives in memory. It's not one big number. It's a little container with three parts. You've got a sign bit, an exponent for the scale, and then you have this, the 23-bit mantissa. This is where the actual digits, the precision, are stored. Now think about it. The number of real numbers is infinite, but your computer has to squeeze every single one of them into this tiny 23-bit box. And that's exactly where the trouble begins. And this, right here, this just lays out the core conflict perfectly. On one side, you have the ideal world of pure math, infinite precision, where the rules are always the rules. On the other side, you've got the machine, the gritty reality of finite computer hardware, where that 23-bit limit means every single calculation is a tiny compromise, a potential rounding error that can break those perfect laws. All right, time to open our first case file. We're going to investigate non-associativity, an anomaly I call the Vanishing Act. Why? Because, and I'm not kidding, the order of operations can make a number literally, poof, disappear. So for this case, we've got two key players. First, we have a large number, let's call it big, which is 1 million. And our second variable, small, is just 1/100th. And it's this huge difference in their scale. That's the key to the whole magic trick. So what happens when we tell the computer, hey, add big and small together? Well, to do the math, the processor has to line up their exponents. But because big is so massive, small has to be shifted way over to the right. It gets shifted so far that its bits literally fall right off the end of that 23-bit mantissa. They get pushed out the door, into the void, they're just gone. The result? 1 million plus 0.01 is 1 million. The small number has completely vanished. But watch this. What if we just change the order? What if we do big plus small plus small? See, first the processor adds the two small numbers together. Their exponents are the same, so no shifting, no lost data. Now we have 0.02. And that result, that 0.02, it's just big enough to get its foot in the door when we add it to big. It manages to nudge that last digit of precision. The FPU is forced to see it, and we actually get the right answer. It's the same numbers, but a totally different result. So yeah, order really matters. So why should you care about this little math trick? Well, one word, determinism. In a multiplayer game, you need the server and every player's computer to get the exact same answer every single time. But what if the server calculates your position one way and your client does it in a slightly different order? Those tiny rounding errors start to build up. Pretty soon, the server thinks you're here, but your computer thinks you're a millimeter to the left. After thousands of calculations, you're in different worlds. It's called world desynchronization. You're basically shooting at ghosts in a parallel universe. Okay, that first case was weird. But this second one? This one is genuinely dangerous. Welcome to the precision cliff, also known as catastrophic cancellation. And this isn't about data vanishing. This is worse. This is about perfectly good data being turned into absolute garbage in a single step. And this graph says it all. We're starting up here, in the green. Everything's great. We've got a healthy 23 bits of reliable information. Then, we perform one single subtraction of two very similar numbers, and bam! We fall right off a cliff. We're in the red zone. Our effective precision has plummeted to just 3 bits. All of our useful data, it's just gone. So, what causes this disaster? Well, the setup for this crime is very specific. It happens when you subtract two numbers that are really big, but also almost identical to each other. Think of two GPS coordinates that are just millimeters apart. All the important information, that critical difference, is buried way, way down in those last few digits. Now let's zoom in to the bit level and see the crime as it happens. Look at this. All these bits at the front of our two numbers, they're identical. So when you subtract them, they just annihilate each other. Poof, wiped out. All that's left is this tiny little fragment of a number from the very end. The number that's left over might be mathematically correct, but it's a ghost. Its internal structure has been completely devastated.
But here's where it gets really sneaky. The hardware has a rule. It hates seeing a number that starts with a bunch of zeros, so it has a reflex. It normalizes the result. It takes those few remaining good bits, shoves them all the way to the left, and then, to cover its tracks, it fills the huge empty space it just created with fake zeros. This is phantom data. It's a total lie, giving you the illusion of high precision where there is absolutely nothing.
And the real-world impact of this lie? Well, it can be explosive. Literally. Imagine a physics engine in a racing game. It gets one of these corrupted numbers to calculate a car's velocity. It sees all those fake zeros and thinks it has a super precise, very large value. It doesn't know it's garbage. So based on this phantom data, it decides the car should have an insane amount of energy. And what happens? Boom, the car just violently explodes, creating energy from nothing. So we've examined the evidence from both of our case files. It's time to deliver the verdict. And it's this. The bizarre behavior of floating point numbers demands a whole new level of awareness from anyone who builds software. Let's just put it all on the evidence board. Case file number 1, our Vanishing Act, is caused by a huge difference in scale between numbers, and it results in data getting lost. Case file number 2, the precision cliff, is the opposite. It's caused by numbers being too similar, and it results in the computer making up fake data out of thin air. Two totally different causes, but two equally dangerous outcomes. Ultimately, the big takeaway here is pretty simple. The math inside your computer is not the same math you learned in school. You just can't trust it blindly. It's a huge structural risk. To build stable, reliable systems, you have to understand this hidden, weird reality happening at the bit level. Which, of course, brings us to the final big question. If this problem is literally baked into the silicon, what in the world can you do about it? Well, that's what we'll get into next time. In our next explainer, we'll explore things like the FMA solution and Kahan-style error recovery. Stay tuned.